This is part 6 to the section 4.3, 4.2, 4.3 videos, and in this I will cover examples about evaluating definite integrals. And right now we just know how to find definite integrals using the limit definition. So at the end of part 5, or the last half of part 5, I use this limit definition. So this isn't anything really new. So I use this in an example in part 5. It's just the definite integrals from, and it's called the definite integral of f of x from a to b is defined to be this limit, is how that's read. And this only represents area if the function f of x is positive on the integral from a to b. So in other words, the integral, definite integral of f of x from a to b can be negative. So this is called the definite integral of f of x. Oh, I don't know why I wrote f of a. So f of x from x equals a to x equals b. All right, and so we're going to do these two examples. They're from 4.3, and it's going to evaluate the definite integrals. And I'll be using that limit definition, which I've used, last video, and then I went over it in previous videos before. Now, for number 5, I think it helps to visualize what's going on here. And this is a graph for number 5. And your function f of x is what's inside of the integral sign. So our f of x is equal to 8. It's a constant function. And so a constant function is just a horizontal line. And the a to b part, so the 2 to 6, so the bounds of the integral give you the interval from a to b. So 2 is called the lower limit of integration, 6 is called the upper limit of integration. But the point is that I go from 2 to 6 for the function f of x equal to 8. And what we're trying to find, since our function is positive, we're finding the area that's represented in purple. We're finding that rectangle. Going from 2 to 6, so that's the base, and then the height of it is 8. So you could use regular formula that we already know. Just because this is I wanted to do a simple example, but we will still use the limit definition to get the same answer, because the limit definition can be applied to any particular continuous function. This is just an easy one where we could know, well, it's that purple shaded region's a rectangle. The area of the rectangle, base times height. That base, 6 minus 2 is 4. And then the height, so that's 8. So it's 4 times 8. So 32. So at least right now, we should get 32 as our answer when we're doing this definite integral. All right, so again, this is just a simple example where we already know a formula to find that area, and it represents an area because our function f of x is positive. But now I'm going to go into using the limit definition, and at least we know what the answer needs to be. So the answer needs to be 32. All right, so that's what we're doing for number 5. And so our function f of x is 8. The bounds 2 and 6 give us the closed interval 2 to 6. And we know that the limit definition So the definite integral is n goes to infinity of that Riemann sum. All right, so first I'll find the sum. Like I did in the previous video. So first find the Riemann sum and then apply the limit as n goes to infinity. And that'll be our answer. That'll give us, that's what the definite integral should be equal to. Okay, so delta x, that's b minus a over n. Well, our interval is 2 to 6. And so it's going to be 6 minus 2 over n. So that's 4 over n. All right, that's the width of the rectangles if we were to think of it like that. So delta x is 4 over n, so I'll go ahead and circle that. And I'm going to use the right endpoints for CI. That's a plus I times delta x. Well, that's CI is going to equal, well, a is 2, so that's going to be 2 plus I times 4 over n. Now notice our function though is 8. So in other words, no matter what we plug in for the input, we're always going to get 8 for the output. So no matter what we plug in, we always get 8. So f of CI is actually just 8. Right, because there's no x that I would substitute in that whole thing, 2 plus 4 over n times I into, because it's just 8. So that's what we use for f of CI. All right, so plug those into the Riemann sum. So f of CI is 8. So we have 8 times delta x. Well, delta x is 4 over n. Well, 4 times 8, so that's 32. So we have 32 over n. Now, we know from the summation formula from Theorem 4.2, we know if we take this sum from I to n of some value c, we get c times n, where c is a constant. In this case, since 32 over n doesn't have I at all, that's like our c. So it's going to be 32 over n times n. And then the n's divide out, so you just get 32. All right, and that's what we get. Now there's no n involved. Let me circle this. This is the Riemann sum. Notice there's no n. So As n goes to infinity, this thing is just 32. So the sum goes to 32. Because there's no n that we plug in, and so it's just always just going to be 32. So the integral 2 to 6 of 8 dx, which is the limit n goes to infinity of the Riemann sum, which we got the Riemann sum to be 32. I'm getting stuff mixed up. Right, so that was limit n goes to infinity. We got the Riemann sum to be 32. Well, there's no n involved, so we just get 32. All right, and like I said before, just we drew the graph as the intuition of what's going on here. And intuitively, it's just the area of that rectangle, which is 32. But we applied the limit definition here to get the same answer. The next one, number 7. So our function's x cubed. The bounds of the integral are -1 to 1. So that gives us the closed interval -1 to 1. And just to think about what its graph, the cubic function's graph. All right, so the cube function looks like that. And if we're going from like, let's see, so that's 1 cubed is 1, and then -1 cubed is -1. So just as far as what it would look like, what we're trying to find. That's what we're trying to find. Now this isn't, since it has some negative value to the graph, the function lies below the x-axis for a portion. We can't say it represents area, but just to see what it looks like, that's what it's going to look like. Okay. So using our definition, -1 to 1, the x cubed dx is going to be the limit n goes to infinity. So I'm just using the limit definition of fci times delta x. And again, I forgot to write the summation sign. Again, I'm going to find this first. And then apply the limit at the end. All right, so I'll just write the function was x cubed. And we have -1 to 1. So delta x is b minus a over n. In case it's 1 minus -1 over n. So that's 2 over n. All right, so that's what delta x is. And so my subintervals, I'll usually write endpoints of the subintervals. That's easier, in my opinion, to do that instead of left endpoints. And the general formula for the right endpoints of each subinterval is a plus ci is equal to a plus I times delta x. In this case, a is -1. This is -1 plus I times 2 over n. Sorry, ci -1 plus 2 over n times I. Now I plug this into the function to get f of ci. So f of ci, instead of x cubed, that's -1 plus 2 over n times I cubed. All right, and so we have to expand this. All right, and the way I expand it, so that's -1 plus 2 over n times I squared, and then times -1 plus 2 over n times I. They know from algebra, if you have a plus b squared, that's going to be a squared plus 2ab plus b squared. Our a is -1, and then our b is the 2n times 2 over n times I. So when we do -1, it's 2 over n times I. That's going to be -1 squared plus 2 times -1 times b. In this case is 2 over n times I. And then plus b squared. That's plus 2 over n times I squared. And so that's going to be -1 squared is 1. And then we have 2 times -1 times 2 is -4. So that's -4 over n times I. And then 2 over n I. And then I square that. That's plus 4 over n squared I squared. All right, that is just the first piece to this puzzle, I guess. This is just that part. So I need to multiply it by -1 plus 2 over n times I. All right, so I'm going to use distribution. And I'll try to use different colors. So first I distribute -1. So that's going to give me -1 times 1 is -1. -1 times -4 over ni, that's positive 4 over ni. And then -1 times 4 over n squared I squared is -4 over n squared I squared. And then I distribute 2 over n times I. With 2 over n times I, that's going to, times 1 is 2 over n times I. And I'm going to write that below the 4 over n times I, since they're like terms, because they have the I as our common variable. So that was the result of doing 2 over n I times 1. Now I do 2 over n I times -4 over n I. Well, 2 times 4, that's going to give you 8. So it's going to be -8 over n squared and then I times I is I squared. And I wrote it directly below the one for negative 4 over n squared I squared because they're like terms. Now I'm doing 2 over ni times 4 over n squared I squared. So 2 times 4, that's 8. And then n times n squared is n cubed. And then I cubed. So then I just add all of that. So f of ci is going to equal negative 1 and then plus 6 over n I minus 12 over n squared I squared and then plus 8 over n cubed I cubed. All right, so this was just algebra to find f of ci. It's just since it was cubed, it was a good bit of algebra. So that's what I'm plugging in. So I have that and then the 2 over n. So our Riemann sum is going to be the following. So I'll put in orange is what f of ci is. Okay, so that's all of f of ci. And then times delta x. Delta x, I believe, was 2 over n. Yeah. All right, so we have this beast that we need to find the sum of. Since everything's being multiplied by 2 over n, I'm going to go ahead and factor the 2 over n in front of the summation. So for each component, I can break it up into its own summation, right? Because I have just a general rule is that anytime I have a plus b, you can break it up as the summation of a plus the summation of b. So for all of this, I'm going to break it up into its own summation. But since it's all being multiplied by 2 over n, I'll put it in brackets. So put each component as its own summation, and then I'm going to apply one of our rules so that you could distribute out any constant, and I want to distribute it out so that I have only I as part of the summations. Now for the first one, we have -1, summation of -1. I know from the theorem 4.2, so let me go ahead and just write down all the formulas that we're going to use. And it looks like we have I squared, I cubed, and the case for -1. So we're going to use all 4 formulas. All right, so that's what I'm using. I'm using every single one. The first one, where it's negative one's like C in this case, so I'm using rule 1. And so it'll be -1 times n is what that turns into. All right, so this will be like -1 times n is -n. And then I'll pull out the 6 over n in front. And then I'll pull out the -12 over n squared. So it only has I squared in the summation. And then I'll pull out the 8 over n cubed. Now I just apply each summation with the corresponding formula. All right, so this summation of I based on our summation formulas is n times n plus 1 over 2. Okay, then minus 12 over n squared. And then times the summation of I squared. And that's going to be n times n plus 1 times 2n plus 1 over 6. And then I have 8 over n cubed. And then the summation of I cubed is n squared times n plus 1 squared over 4. All right, so now the summation signs are all gone and it's a matter of simplifying. And of course, I'm going to go in the brackets first. All right, so I'll leave the 2 over n, and then -n, and then plus, and now I'll do some simplifying. Well, I can divide in those n's, and then I can also do 6 divided by 2, which is 3. So that gives me 3 times n plus 1. All right, because the n's divided out, and then the 2 divided about, because 6 divided by 2 is 3. All right, now the next thing. Well, I can divide out n from n squared, so that's just 12 over n, but then I can also do 12 divided by 6 is 2. You have 2 over n times n plus 1 times 2n plus 1. All right, and then plus, and then for this, I can divide out n squared from n cubed to make that just n. And then 8 divided by 4 is 2. That gives me 2 over n, and then n plus 1 squared. Okay, let's see. No, this is just from experience as far as simplifying stuff. Now you could distribute 3, you could distribute 2 over n. To me, to reduce the amount of work, I noticed that I have n plus 1 for these 3 terms. So what I'm going to do is factor out n plus 1. All right, so I'll factor out n plus 1. And what is that going to give me? That's going to give me, I'm going to put in parentheses the result after I factor out n plus 1 from the 3 terms that have underlined n plus 1. So this one's going to give me 3. And then the next one I have negative 2 over n, and then 2n plus 1. And then the last one I took out of n plus 1, so that's going to just be 2 over n times n plus 1. All right, and I just did that just so it's less algebra steps to do. Let's see, so right now I'm going to keep n plus 1 in parentheses. I can't just add negative n and n to cancel those out, because n plus 1 is its own factor. All right, so what I'm going to do now, let's see, so I'll distribute negative 2 over n here, and then 2 over n here. That's going to give me 3. Negative 2 over n times 2n, well, the n's cancel out, so you just have 2 times 2 is 4, so that's minus 4. Negative 2 over n times 1, so it's negative 2 over n. So that takes care of that. And then the next one I do 2 over n times n. The n's cancel out, so you just get 2. And then I do 2 over n times 1, which is 2 over n. All right, again, that's the result of distributing the 2 over n's. Now I just combine like terms. So this problem just takes a lot of algebra. All right, what are my like terms? Let's see, so I have 3 minus 4, that's negative 1, and then I have plus 2. So negative 1 plus 2, that's going to give me, so 2 minus 1 is 1. And then I have, let's see, I have a negative 2n and a positive 2n. So these cancel out. So it's just 1. All right, so that's the beauty of doing these factoring. So hopefully that makes sense. I factored out the n plus 1 from those 3 terms, and the result that I put in parentheses, it was way easier, in my opinion, to simplify than it would be if you distributed 3 times n, 3 times 1, and so forth. Just double check the algebra. So 3 minus 4 is negative 1, and then plus 2, so that's 2 minus 1 is 1. And then the negative 2 and positive 2 and cancel out. Yeah, I think it's good. Should be good. All right, so I have 2 over n, and then brackets, negative n. N plus 1 times 1 is n plus 1, so I could just go ahead and just drop the parentheses and write it as n plus 1. Then I could do negative n plus n, those cancel out, so you just have 1. And you do 1 times 2 over n is 2 over n. All right, so finally, this is the result for the Riemann sum. So we're pretty much there. We just kind of take the limit. So right now we have the Riemann sum. That came out to be 2 over n. So last, we just take the limit as n goes to infinity. All right, so the indefinite integral, and our definite integral is negative 1 to 1 x cubed dx. And that was equivalent to taking the limit of that Riemann sum. And we got the Riemann sum to be 2 over n. So this is equal to the limit n goes to infinity of 2 over n. Well, since it's going to infinity, 2 over n goes to 0. That equals 0. So our answer for the definite integral is 0. All right, so that was a lot of steps, a lot of algebra to get to our result. All right, and just to recap, I'm not going to go through every single detail, but what we did first was, all right, so we found delta x, which is 2 over n. Then I find the CI values like I've always been doing for these, and that's using the right endpoints. And I got the right endpoints to be -1 plus 2 over n times I. And then I plug that into x cubed, and that gives me 1 minus 4 over n, or actually no, that gave me this, what I circled in yellow. So f of ci, after I simplified everything, -1 plus 6 over n times I minus 12 over n squared I squared plus 8n cubed I cubed is the result of plugging in what I had for ci being -1 plus 2 over n times I. So then I just plugged in the corresponding values into the Riemann sum for f of ci and delta x. And then I did a bunch of algebra simplifying this Riemann sum. And that involved using the Theorem 4.2. And I happened to use all 4 formulas for this case. And then after I simplified all this, did some canceling, I got 2 over n. All right, that's what the sum is. The Riemann sum is 2 over n. So the last thing we need to do is take the limit. So the definite integral from -1 to 1 of x cubed dx is equal to the limit of the Riemann sum, which the Riemann sum is 2 over n. So that limit is 0. All right, so that definite integral is equal to 0. And that's where I'll stop the video. And next time, I'm going to start the next section, which is a very crucial section. I'm going to start 4.4 and start off with the fundamental theorem of calculus. All right, so what we build up to is in the next section. And just as a preview or just a quick synopsis, I guess, it's essentially you don't have to apply this limit anymore. So all that work, we'll find that there's a way to get the same answer without having to do that limit. It's very similar to when we did derivatives, where we first learned the limit definition of a derivative, and then we learned the rules, so that when we learned the rules, we didn't have to no longer keep applying the limit definition. All right, so that's it for section 4.2/4.3.